I would like to give my talk in Italian, but that would be painful for everybody involved. My name is John. I'm here to talk about the kernel. Got a lot of stuff to get into, so kind of get right into it. This is what the Linux kernel community has been up to over the course of the past year and a few months. All right, as you can see, we put out 6 major releases. These are all big releases with lots of new features and so on. Each one had at least 13,000 changes put into it. So a fair number of releases, a number of changes, especially considering that these releases all happened over the course of about 9 or 10 weeks each. The kernel community, as you can see, has been busy, but if you've seen my talks before, you know that I've been putting up a slide like this for quite a while. It's actually gotten kind of boring because we have seen by now that the kernel community works as a pretty well-tuned machine. You know when the next release is going to come out. In fact, we're pretty well convinced at this point that 4.20 will come out on Christmas because we can predict it that well. So I can put up a chart like this, but it's kind of like putting up a table of sunrise times, for example. It may be useful, but it's not got a lot of surprises in it. That said, there is one thing I wish to point out here, which is the 4.15 release, which took 11 weeks to come out. This is the first time we have taken more than 10 weeks to produce a kernel release since 3.1 came out in 2011, 7 years ago. So 3.1 was delayed because kernel.org got broken into, and we had to completely redo our development infrastructure to cope with that. So something equally significant, one might think, must have happened to delay 4.15. Now, sometimes that's just Linux needing to go diving or something, but not this time. This time we had, of course, the advent of Meltdown and Spectre during the 4.15 development cycle. So I'm not going to talk much about the actual nature of these vulnerabilities. They've been well covered elsewhere. I can suggest a website if you need to read about them. But I want to talk a bit about how these problems interacted with our development community. Because even though, in a real sense, Meltdown and Spectre are emblematic of a totally new class of vulnerability that we have to deal with. In fact, I was assured from Intel this is a brand new class of stuff that's never happened before. But as far as the kernel community is concerned, these things really just look like more software vulnerabilities. We've got a hole in the system. We have to bring together the experts in the part of the system that are relevant to this particular vulnerability and fix it in software, right? It's the same sort of thing. And we have a process for dealing with this sort of stuff. The problem, of course, is that for Meltdown and Spectre, this process was not followed at all. Rather than our usual community-oriented process for dealing with security problems, what we got was a whole lot of secrecy. These vulnerabilities were discovered in the early summer of 2017. The Linux kernel community was not told about it until very near the end of October in that same year. So this had been going on for quite some time before we were even given a heads up that there was a problem here. And even then, the amount of information that was given to us was not as much as we needed. And when that information was given, we were also subjected to a great deal of siloing in that people had to sign non-disclosure agreements, and developers within the kernel community were not allowed to talk to each other about how they were handling this sort of stuff, which is not how we work normally. So we had everybody off working on their own, and there were some real consequences to this, including a lot of fragmentation among the distributors. If you look at what the distributors shipped when Meltdown and Spectre were disclosed, you'll see that they all shipped something different. And the reason that they did that was because they were not able to work together on the solutions that they were going to ship until very close to when this disclosure happened. So, and some of the things they shipped were rather better than some of the others. This is actually worth looking at in a little bit more detail because there's an interesting natural experiment that was run as part of the handling of Meltdown and Spectre. If you look at Meltdown, one of the interesting things about Meltdown was that the fixes for Meltdown were developed in public. They were developed on the kernel mailing list. Even though nobody was told what the problem was that was being fixed, the fixes themselves could be posted publicly because they were able to come up with a cover story essentially to do that. So as soon as these patches were posted, we got a lot of people working on them, including people who were not privy to the details of the vulnerability at all, The fixes improved a great deal over the course of the 2 months that they were discussed on the list, so that when the vulnerability was disclosed, the Meltdown fixes, kernel page table isolation in particular, were in pretty good shape. They were in the mainline kernel, and while I wouldn't say they were bug-free, they were getting there. And so everybody shipped pretty much the same thing when the vulnerability came out, and those fixes did not have to evolve much after that. Spectre, instead, was addressed totally in private. For various reasons, those fixes could not be disclosed publicly without actually disclosing the vulnerability itself. But even the people who were working on this problem weren't really able to work together on it and to bring in the people they needed. So as a result, the fixes that were developed for Spectre were not ready at the time of disclosure. Everybody shipped something different, and whatever your particular distributor shipped did not make it into the mainline kernel in anything resembling that form. And when the public discussion happened on the Spectre vulnerabilities, all that work had to be tossed out and redone from the beginning in a way that was really suitable for the mainline kernel. So we saw a big difference here in what happened depending on whether our community process was followed or not. And some of the consequences of that are still reverberating in the community, as I'll come back to in a moment. In fact, I'll come back to it now. This is a quote, actually just came out last week in response to some of the stuff you may have seen about the STIBP patches, which are more Spectre-related patches that actually just made it into the mainline yesterday. We went through a whole routine there because the initial fixes that went into the kernel caused some huge performance regressions and made a big fuss. And as this was resolved, Paolo Bonzini said the fact that this stuff made it through the maintainers is a late effect of the secrecy that affected us nearly a year ago. We still haven't really worked through all of this stuff because we just have not been told all the things that we really needed to know to handle this stuff properly. So consequences included fragmentation, also include a whole lot of developer burnout and frustration. I think that a lot of people don't realize just how hard a small group of people in our community worked to make sure that we were ready for the disclosure of these vulnerabilities. These include that grumpy guy sitting over there towards the back on that side, and quite a few other people. I think we owe them a big hand of applause for the work that they did. But there was a great cost to this in terms of what these people had to go through during their holiday season and so on to do this, and a lot of frustration that every now and then popped out in public, even though they managed to mostly keep it to themselves most of the time. It was not much fun for anybody involved. And then finally, a lot of people were left out in the cold, and I mean this in a couple of ways. Some of the major distributors like Red Hat and SUSE were ready when the disclosure happened. They had fixes to ship, updates to ship to people. Other distributors like Debian were only informed just a little bit before the disclosure happened, and they were not ready. And some other distributors, Gentoo, for example, were completely blindsided by this stuff. They were not able to have an answer for their users when the vulnerabilities came out. This also happened in the commercial world. If you look back at Disclosure Day, we got all these really nice, reassuring press releases from companies like Amazon and Google and Microsoft saying, all of our users are fully protected from the very first day, which was more or less true. But if you had your website, say, one of the so-called Tier 2 providers, like some of us did, those providers, too, were blindsided. They had no idea what was coming, and they had no chance to prepare ahead of time. Now, the cloud computing marketplace is very concentrated now. There are only a small number of big providers. If we create a world where only those very big providers have access to crucial security information like this, the only result can be further concentration of this market. And that's not something I think that any of us really want to see. But that's what we're working towards if we do things in this way. The good news is that at least some of the lessons hopefully have been learned. I've been told that the handling of the L1 terminal fault vulnerability, which was disclosed in September, was better. There were a lot of discussions in the community and discussions with vendors and so on to try to avoid the mess that happened with Meltdown and Spectre and do things better in the future. The bad news, though, is that even though we like to think that we're all out here developing and running free software, we're completely in control of our systems, but this software that we develop has to run on hardware, and this hardware turns out to be a black box that's supposed to be living up to a particular specification, but isn't always. If you've ever read the works of Herbert Simon, one of the things he said was, the way to find out what's inside a black box is to make it fail. Well, we've done this, and when we look inside the black box, we're not necessarily happy with everything that we see in there, right? This black box of hardware turns out to contain a whole bunch of what is essentially proprietary software in its own right that has a lot of the same sorts of pathologies that afflict proprietary software elsewhere, and is not necessarily something that we can really count on to run our free software the way we expect it to be run. So we haven't, I think, fully come to terms with what it means to live in a world where we can't trust our hardware as much as we thought that we could. So how we're going to deal with that is going to be interesting to see. If we think about in the near-term future, I just threw together a couple of notes here. For the most part, if you're running on your own hardware with that untrusted software, you can, for the most part, relax. Not fully, but for the most part. If you're more worried, disable hyperthreading on your systems. Hyperthreading is essentially two fake processors sharing one real processor in the hardware. And it is perhaps unlikely that this will ever be possible to do without the creation of covert channels between those two virtual processors running there. So people who are highly security sensitive are disabling this feature and taking the performance cost that comes with it. Further in the future, one thing that I think is just worth a look is a feature called co-scheduling that is being worked on out there. Co-scheduling allows the system administrator to set up trust boundaries in the system saying, this group of processes trust each other, so they can be allowed to run on the same core, and we're not worried that there may be communications channels between them. These other processes over here, they don't trust each other. They cannot run simultaneously in this way. This is a hard feature to implement without wrecking the scheduler. The scheduler developers get kind of grumpy when it even comes up. But it's, I think, the kind of thing that we're going to have to do when we realize that our hardware cannot fully enforce our trust boundaries for us. And we have to take some of that into our own hands. And then finally, of course, this is something I'll come back to. Run current kernels. If you're not running current kernels, you have much worse problems than Meltdown and Spectre, really. But you have these problems, too. And so you want to stay up to date with what the community is doing. And so along those lines, I'm going to talk for a moment on the stable kernel process. Here's what the stable kernel group, which basically consists of Greg Hartman, has been up to, or at least the status of where they were about 2 weeks ago when I made this slide. It is, of course, highly obsolete now. But there were, at that time, 6 kernels that he was maintaining with stable updates. That's down to 5, because 4.18 has gone out of support now. And you can see that there's an awful lot of stuff going into these stable kernel updates. 4.9 has received over 10,000 fixes over the course of its maintenance, over just about 2 years. That's a lot of important fixes. That's the sort of stuff that you want to have if you were running a system that you count on for anything in particular. So the stable kernel process, and there are some issues with this. I'll get to a couple of them. But for the most part, it runs pretty smoothly as well, putting out 1 or 2 or sometimes even 3 updates every week full of important stuff. Some of the things that we're trying to improve include increasing the support period. For years, the support period for a long-term support stable kernel was 2 years, which seems like a while. But if you're working, for example, in the Android world, 2 years is about the time it takes for a kernel release to actually get into a device and into a user's hands. It's really that slow. So 2 years of support isn't really enough, because just when people start really using that kernel, it goes out of support. So Greg has agreed to support 4.4 through 2022, 4.9 through 2023. That's 6 years of support, which is quite a bit more, which will be helpful in that regard. Then, if you want to be really crazy, there's a group called the Civil Infrastructure Platform that is looking at supporting kernels for periods of 10 to 20 years, which is not going to be an easy thing to do. They are looking at systems like elevators or building heating systems or automobiles, where you've deployed a Linux kernel into a system and it has to run for a long time. and you would like it to run with a supported kernel, if at all possible. So I wish them luck with that. It's not going to be easy to do. The other thing we're trying to do, of course, is to get more fixes into our stable kernels. If you look at 4.9, as I said, there's been over 10,000 fixes that have gone into that kernel. But during the same period of time, we've had almost 150,000 changes going into the mainline kernel. It's fairly likely that among those other 140,000 changes, there are some important fixes that you would want to have in your stable kernel as well. Right? It's pretty unlikely that we have gotten them all into the stable kernels. So there's been work done to improve developer discipline and getting fixes, important fixes, into the stable kernels. There are even people like Sasha Levin who's put together a machine learning system that's trying to automatically recognize patches that look like fixes and to kick them out for review for merging into the stable kernels as well. And this has increased the patch flow into the stable kernels quite a bit. This is not uncontroversial in that some people think that too much stuff now is going into the stable kernels and creating things, well, creating regressions, breaking things. We have had some incidents now where stable kernels have been released with a serious problem that has affected users. And you don't want that. Stable kernels are supposed to be stable, after all. So if you ship things, if you ship bugs, this is not good. Now, you're never ever going to merge thousands of patches into a particular kernel release and not have the occasional problem. That's just the nature of the beast. But with any luck, you can do better than we're doing now. There's lots of things to do, including better testing, which I'll get back to more to try to deal with that. But the other problem that has come out with stable kernels comes back to things like Meltdown and Spectre. There were a whole lot of patches needed to address these problems, and they were not simple patches. These were huge rewritings of how the memory management subsystem works and how system call entry works and things like that. They were invasive. They were major changes. They're not the things that you would want to put into something you would consider to be a stable kernel. So this is a problem even for your most recent stable releases. If you're now trying to take these huge invasive fixes and backport them to, I don't know, 3.18 or something like that, you now have hundreds of thousands of intervening changes that have happened in that kernel. They've changed much of the code that you're trying to patch, so those backports become very difficult to do. In fact, it gets hard enough that even as far back as 4.4, not all of these fixes have actually been backported because it's just too hard. It's just too much work to do to try to keep the result even remotely stable after that. So this kind of issue is amplifying the voices that have been asking for a while whether this whole idea of maintaining kernels for a long time is broken in its concept. If this is really something that we can try to do over the long term. Certain people have been pretty clear about it, and saying the illusion of supporting a product for 20 years with software from 20 years ago has been destroyed, but people still cling to it. And people do. We're getting better about it. But if you have some kernel that was released years ago and you've applied thousands of fixes to it, you have something with the same major version number, but it is not that kernel that was released. And it's not necessarily going to be an easy thing to stabilize and support. So this model, I think, really needs to be rethought. And if we're thinking about building smarter devices, for example, that's one thing that we have to be thinking about, is building smarter devices with current kernels. That's really the model that people are coming to here, where even if you've got some older device, when you have to update it to a current kernel, or at least update it to the current long-term supported kernel. Because that's the kernel that's got all the latest fixtures, including the ones that may not have been kicked out for older stable kernel releases, and a whole lot of features that you may want too. Things like security features, for example, that are in there. It is, in other words, the best kernel that we as a community know how to make. And that's what you should be running on your devices, even if it's an older device. So it's a hard sell, this idea, for a lot of people, but I think a fair amount of the vendor community is beginning to understand this. And I think we'll see things moving along this front. And again, I will come back to this in a moment in the Android context. But there is one remaining problem with this idea, which is that if we're telling people you have a 20-year-old computer, but we want you to run a current kernel on it, we need to be absolutely sure that your 20-year-old hardware still works in that current kernel. And this is pretty hard to do in a world where no developers actually have that hardware anymore. So they can't test it, they can't make sure that they didn't inadvertently break it. And this is an ongoing problem that we're still trying to figure out how to solve properly. I assume we'll get there, but we still have to work on it. One of the answers to many of our problems actually is testing, which is the next thing I want to talk about. The kernel community for a long time was pretty famously devoid of any kind of organized testing efforts. Or to put it another way, the way we did our testing was to make a release and wait for everybody to run it and tell us what was broken. Seriously. And to an extent, it's always going to have to be that way, just because the sheer variety of hardware and the sheer variety of workloads that are out there are something that no developer can have in-house. In fact, that no company can have in-house. There's just too much stuff out there, so there's always going to be surprises when we release a kernel. That said, we can do an awful lot better than we have. We can find a lot of problems that we have not been finding so far. So in recent years, we've seen a lot of testing efforts start up, including things like the zero-day robot, which picks up patches off of the mailing lists and does build and boot tests on it. And then you get a cheery little email saying, I love your patch, but it broke. And you can fix it. And it's found a whole lot of problems in patches before they ever get into even a subsystem tree, much less the main line. Kernel CI is a distributed testing effort trying to test on a whole lot of different hardware. K-self-test is a set of unit tests built into the kernel itself we have now. And there's another initiative out there called K-unit that will likely get merged as well. Syzbot is doing a lot of fuzz testing on pre-release kernels and posting the results of that whenever they find a bug and breaks things. The Linux kernel functional testing initiative is being run out of Linaro. And again, doing more testing. And there's a whole lot of internal efforts at vendors as well. For example, Google is running extensive tests on the various release candidate kernels in the Android context and beyond. And once again, either putting out bug reports or even fixes for the things they find. So this has helped us to find a lot of problems before things get to users and allowed us to release much better kernels. It's still not where we really need to be. I think we need a lot more testing than we have. But one has to start somewhere, and we have finally done that. So that's some good news in my mind, that we have improved something that we were bad at for a long time here. So moving away from process stuff for a second, there's one technical area that I want to talk about because there's a lot of interesting things happening here. And I'm not sure that people fully understand all the implications of what BPF, the Berkeley packet filter, means. BPF is an in-kernel virtual machine. It's essentially an emulated computer that allows user space to load a program written for this computer into the kernel and run the program in the kernel's context. Now, this sounds like perhaps a fairly dangerous thing to do for the kernel to accept code like that and run it that way. So to address this, BPF includes a built-in verifier. Whenever a program is presented to the kernel, the verifier will perform a static analysis on it. It will make sure that it will terminate by virtue of not having any loops at all, for example. It will make sure that it cannot access any memory that is outside of the memory that is explicitly given to it to work with. And it does that by actually doing a simulated run of the program and seeing what the limits are, and so on. It's quite a complex bit of code. And but if it works, and of course a complex bit of code like that's never going to have bugs, then we can assume that a given BPF program is actually safe for the kernel to run. Along with that, it has a built-in just-in-time compiler. So even though these programs are not written for the local architecture, they're written for an abstract architecture, those programs are compiled down to whatever your local system is. So they will run very fast. And that is important because BPF programs are showing up in an awful lot of contexts, including, for example, in the making of security policy decisions. The secure computing mechanism has allowed the use of BPF to decide which system calls a sandbox program can make for some years now. That's not new. The landlocked security module is still out of tree, That allows attaching programs to specific system calls so that things can be looked at in more detail and security policy decisions can be made in that way in the kernel in a much more flexible way than anything that's in there now. You see it in protocol implementations. Every infrared remote control speaks its own protocol, right? They can't, of course, say the same thing because you hit the play button. So we could build into the kernel a whole bunch, like hundreds of protocol modules to understand these. Or else we could allow the loading of a little BPF program that understands only the specific protocol that your remote control understands. And in fact, we now have that capability as of earlier this year to do that and to get all these protocol modules out of the kernel otherwise. Instrumentation and tracing are now using BPF heavily, in that you can load BPF programs, attach them to trace points, and use that to boil down and aggregate data and get that data out all at quite high speed. There's a whole impressive series of tools that have been written around this. You can find them in the BPF compiler collection to deal with this kind of stuff. And other tracing solutions are being ported to make use of it as well. There's a lot going on in this area. This is an area of very active development. You see it, of course, in things like packet filtering, which is unsurprising because BPF is the Berkeley packet filter, after all. But BP filter goes beyond that by ripping out the entire net filter IP tables firewalling mechanism that's in the kernel now and replace it with the ability to run a BPF program to examine packets and make decisions like that. So in a sense, it seems like a loss of functionality, but this BPF program can be very specific to your needs and look at only what you need, and you don't need to drag along this entire firewalling subsystem with it that can do 1,000 things that you don't need to do. So it actually runs faster than using the built-in firewalling code. BP filter is still in a pretty early state. I wouldn't deploy it right now, but that looks very much like the future of Linux firewalling as well. And then there's a thing called the Express Data Path, or XDP, which is an effort in the networking community to win back some of the users that they have lost to user space networking stacks for people who just find in-kernel networking to be too slow. XDP works, at least when you use AFXDP, by creating a whole set of shared memory circular buffers. And rather than processing packets and doing protocol processing in the kernel simply puts these packets directly into these circular buffers. Then user space reads them out of those circular buffers, and all the processing is done in user space. So there's really no processing that is done in the kernel at all. And user space, once again, can do exactly what it needs to do, accessing these packets without the need to make any system calls at all to get to them. But you still need to get the packets into the right circular buffers and filter out the ones you don't want to deal with at all, and so on. So, of course, you load a BPF program that does this, that sort of thing. So this is going to be the future of really low latency networking, I think, is this sort of stuff here. So if you're doing, high-speed trading, something like that, that's what you're going to be using in the future. And it's showing up in other places as well. The summary of this is that BPF is used in a couple of modes. It's used to supplement existing functionality by adding the ability to make policy decisions or whatever, but also to completely replace existing kernel functionality with something else that you've loaded from user space, that you've written to meet your needs, that is not something that some kernel developer thought that you might need. Okay, it allows us to push code into the kernel in a way that we couldn't do before. So this is a significant change, but it actually doesn't end there. In that there's also a lot of work happening to push code in the other direction, out of the kernel and into user space. There's the Express Data Path stuff that I had mentioned before. The secure computing mechanism is likely to gain soon the ability to push policy decisions back out to user space if it's something that's too complicated or too hard to do in the kernel. ELF modules are a mechanism that was added with BP filter to allow the kernel to run specific processing code in process context as a user space process and get that code out of the kernel. User fault FD is something we've had for years now that allows the handling of page faults, which is the kind of a consummate kernel functionality. You can now push that out to user space as well. So a lot of things that were done in the kernel are now being done in user space instead. And this is changing our view of how our systems work. The classic view of a monolithic Unix-like system like Linux is that you've got this hard kernel with distinct boundaries surrounded by user space. and a very narrow path between the two of them. All of this movement of code back and forth is making that boundary porous, so that the shape of the kernel becomes much more amorphous, because you've loaded these BPF modules to do this stuff in the kernel, you've moved this other functionality out to user space. And so the shape of your kernel is going to look very different in the coming years, and very different than what perhaps the kernel developers had in mind when they developed it. It's an interesting change. It's a significant change in how we build our systems, and it's definitely worth watching. All right, different topic here, which is out-of-tree code. Code that may or may not be free software, but which is not in the mainline kernel. How many of you have a phone that runs a Linux kernel? Raise your hands. How many of you are really sure of that? This is a slide that I stole from Tim Bird some years ago, where he went and he looked at the kernels that were shipped in popular handsets at that time, and how many lines of out-of-tree code were shipped in those kernels. And what you see are numbers like 2 or 3 million lines of code. Now, if you think of the Linux kernel as being 20-some million lines of code, you can figure out everything that you don't need for a handset, right, which is most of it. And you have a few million lines of code left over, let's say. Then you add 3 million lines of out-of-tree code. And this is code that's not just adding device drivers. Likely as not, your Linux phone has its own CPU scheduler that was supplied by the SoC manufacturer and isn't using the kernel's scheduler at all. You have something that really isn't recognizably a Linux kernel anymore. It still says Linux. It has a Linux version number, but it's something rather different from that. So there are a lot of fairly unfortunate consequences to this. One of which is that if you are a handset vendor or an SoC vendor, and you've got millions of lines of out-of-tree code that say are all written for the 3.18 kernel, and then you think, okay, I would like to ship a modern kernel because people are saying we should be shipping current kernels. But first I have to forward port my 3 million lines of out-of-tree code. You're not going to do it, and they don't do it. And this is one of the reasons why our devices tend to run old kernels, is because of all of this out-of-tree code that acts as an anchor, holding it back. But there's also the simple problem that you cannot run mainline kernels on Android devices. So you lock out the hobbyists, who are one of our sources of future kernel developers. You can't update them to current kernels at all, even if you wanted to. Once the manufacturer stops supporting it and stops shipping their own updates, which they usually do a few milliseconds after they stop making it, then you're stuck, right? That device becomes unsupported and insecure, and even in the community, we cannot support it. And there's a whole lot of effort that's wasted supporting this out-of-tree code that really could be working on improving the mainline instead. So it's a sad picture, but there are signs of progress. The Android Oreo release actually mandated that you had to use one of these 3 kernels in devices that you shipped. They're trying to force the vendors to something resembling a current kernel, even if 3.18 isn't exactly current and wasn't even then. The Android Pie release actually took this another step further, so that you not only have to ship a particular major release of the kernel, but a particular stable update as well. So you can't just ship a 4.4 kernel. It has to be at least 4.4.107. So they're really pushing the vendors to actually ship all of our fixes and our current updates, do the sort of stuff that I was talking about before, try to stay a bit closer to the mainline releases. And the future plan, as I was told just last month at the Linux Plumbers Conference, is to require updates shipped to deployed devices to include the stable updates. They aren't there yet, but they intend to do this in the fairly near future, so that we actually have to get those fixes in our devices. So this is an important step in the right direction to get us closer to mainline kernels on this sort of hardware. This is a step towards smarter devices. Another aspect of this is the Android Common Kernel, which is now the base for the kernels that are shipped on Android devices. They've been working on upstreaming stuff for a while. They now claim there are only about 30 patches applied to it to get from the mainline kernel to the Android Common Kernel, which, if you think about the situation just a few years ago, is a huge step in the right direction, a huge improvement. And along with this is a thing called the generic system image. This is an Android open source project build that has to boot on your particular device if you're going to call this device an Android device, right? It's a test essentially that you have implemented the Android interfaces correctly, including their vendor hardware interfaces. So for the time being, the kernel is not part of this generic system image. This is something that the vendor provides to boot the generic system image on. But the plan is to move the core kernel into the generic system image. So that anything that the vendor is going to supply on top of that has to be supplied as a kernel module. And so you might think, well, that doesn't help things a lot because they're just going to push all of their out-of-tree code into modules. But it's actually a significant change because this forces their out-of-tree code to use the Linux kernel's standard module interface, right? There will be no more substituted CPU schedulers in this world. You cannot do that from a kernel module, for example. And all of this code, it has to adhere to the module interface. And since they have to ship stable updates and keep up with it and forward port it anyway, it's going to be much more mainline ready than this code has been in the past. So there's going to be every incentive for them to get this code upstream. It seems that a number of the vendors have figured out that it is in their interest to do this. So we're not there yet, but we're actually getting closer to a day when the Android problem is behind us. And we can actually run mainline kernels on our mobile and embedded devices. And this is a huge step forward for our community as a whole. It's a great thing. And I hope that everything happens the way that they're trying to drive it in that direction. So I've got one more thing to talk about here, which I couldn't skip given the conversations we've been having in our community in the last few months. And that has to do with conduct and how we behave within the development community. I'm not sure why this has come out, given that we're always fully respectful of each other in the kernel community at all times. But it has. So more seriously, a while back, Alessandro wrote a book and let me then muck with it thereafter. And when O'Reilly went to create the covers for its series of Linux books, they didn't put cute little squirrels on the cover. We didn't get owls or hummingbirds or whatever, right? We got a Wild West theme. And I've never talked to the person who made this decision, but I can only believe that it was deliberate because the kernel community at this time when this was done, which was the late 1990s, was very much a Wild West sort of community. We did things our own way, by our own rules. We solved things by duels in the town square, and so on, right? We definitely did not do things the way the software development world as a whole did things. And this showed itself in an awful lot of ways, right? If you remember back to the days when we had no source code management system, I mean, I don't really know how we made it work back then. We, of course, would not possibly make that work at the scale that we are operating now. And no change tracking. There's still no way to go back to the early kernels and really say where a particular set of code came from, right? All you can do is to try to look at the mailing list and try to figure it out. We had no real release discipline. If you remember back to the 2.whatever days, it took us 3 or 4 years to get a major kernel release out. Imagine where we would be now if we were taking 3 or 4 years to get a kernel release out, right? I don't think that we would have enjoyed the success that we have enjoyed. We didn't really have any rules on user space regression, so we tended to break things between major releases, which really didn't enamor us entirely of our users. As I mentioned before, we didn't really have much in the way of automated testing, that sort of thing. And of course, we had no set of rules about how it was that we thought we should deal with each other in our development community. And that too showed itself in terms of how we interacted with each other. Now, this has improved a lot over the years, even without a code of conduct. The way the kernel community works now, or has worked in recent years, is not the way we worked back in the 1990s, and that's a good thing. But still, there's room for improvement. So, over the years, we have dealt with all of these things, right? We now have source code management and change tracking and all that good stuff. And now, as of September, we also have a code of conduct. We adopted one that was taken from a project called the Contributor Covenant. Not everybody entirely likes that particular project, but you don't have to buy into everything that they're into to agree that we should be dealing with each other in a better sort of way. We have added to it a document that describes how we intend to interpret this code of conduct within the kernel development community. It's clarified a lot of things that essentially say that we want to, for the most part, continue working the way we have worked in the past. That we are not adopting some sort of new agenda that was never something the kernel community wanted to pursue in the past. And the idea, part of the idea behind this interpretation document was to be sure that no group in the future could use this code of conduct to drive the kernel community in directions that we didn't want it to go. So there's still people who worry about this. They worry that the code of conduct means, for example, that we can no longer criticize patches technically and that we're going to have to start accepting code that is not up to our standards. Or they worry that the kernel development just isn't going to be fun anymore as a result of this. And I think that for the most part, we've managed to address these worries, and for the rest, only time will tell. But I can say that this code of conduct has been adopted by people who've been in the kernel community for a long time. We've helped to build it to what it is now. We don't want to see it ruined. We don't want to see the kernel ruined, and we have no intention of allowing that to happen. So I think we're going to be good. I think that in the end, kernel development will still be fun. In fact, if we can manage to be a little bit nicer to each other while we're doing it, it should be even more fun than it was in the past. So I think there's reason for hope there. And with that, I reached the end of what I had to talk about, and I would like to thank you all for your attention. So it looks like we have a minute or two for questions if anybody has anything they would like to ask. Surely somebody has a question. There we go, back there.
Do you think that a block and queue remade with BPF may be conceivable?
Sorry, which made with BPF? You mean something like BFQ redone with BPF?
No. Not to that point. I mean, using BPF
yes.
To move block and queue, turn it into something much more efficient. Is it for something so large? Do you think it might be feasible too?
That is a good question. I'm not sure I fully understand exactly what you want to do, but BPF has invaded a lot of parts of the kernel. There are limits to what you can do with BPF. For example, right now you cannot loop in a BPF program at all. So if you're trying to solve a problem that involves looping, then you won't be able to do it there. And there are various other limitations imposed by the verifier. So BPF can't do everything. We're not going to rewrite the whole kernel in BPF. But it has moved into surprising areas, and I think it may continue to do so in the future. So I don't know if that really answers your question or not. But all right, we had another question back there before.
John, I'm sorry, this is going to be on COC. And I know it's maybe mean, but I still don't get why we adopted a document that has been, and we had to make an interpretation out of that, which has been a very painful process in the last 2 months. And basically, we got with a new code of conduct out of the interpretation model. So is there any reason why the first one has been adopted in first place? And in a way that it has been adopted? I know this may be mean, but...
No, that's a good question. That's a good question. Why did we adopt that particular code of conduct? The reason that we adopted it was really to avoid reinventing our own wheel, right? First of all, for various reasons, we were in a bit of a hurry to do this. But this is a code of conduct that has been adopted by hundreds of projects. And so rather than come out and say that we are so special that we have to do this from scratch, let us go ahead and pick up something that the community as a whole, or maybe not as a whole, but a large part of the community has taken as their particular approach to how we want to behave. And while we may not fully agree with everything that's in the code of conduct, the basic ideas behind it made sense to us at the time. So it seemed better to adopt that than to try to write something new. Right? We had written something new before when we adopted the code of conflict some years ago. And that didn't really go very well for a number of reasons. So that was why. And then the addition of the interpretation document was to try to smooth over the parts that we thought didn't quite fit, but also just to provide some more detail about how it would work in our specific community, which is always going to be a little bit different than any other community out there. So does that answer your question? Anybody else? If not, then I guess we have a break at this point. All right, thank you.
Thank you, Jonathan.